Okay, here we go into chapter 6. Okay, so we're going to talk about the last two gates, and then we'll have all of them essentially. Okay, the first one we're going to talk about is this thing called the exclusive OR gate. And essentially what you do is you take an OR gate and then you negate the combination where you have all of them high, which gives you a high output. So, only one or the others, but not both. Okay? So, if you've got and I believe you can only use 2 input gates for the exclusive OR. You can only exclusive OR 2 inputs. I don't believe there is such thing as a 3 or 4 or whatever, but I mean, I guess you could make one. You could make one out of regular gates. But I know, like in Quartus, you don't have access to a 3 or 4 or 5 input exclusive NOR or exclusive OR. So the exclusive OR says the output is high if either, so you hear the 0, 1 or the 1, 0 condition, that will produce a high in the output, but no longer is the 1, 1. Okay? So, one or the other, but not both. Okay, so that's kind of a special situation. There's no mnemonic device or visual mental image that I can give you for this one. It's just, you just have to remember it's either or, but not both. Okay? If we were going to do that in regular gates, we could do something similar. This is the way it looks, right? X equals not A and B, or X equals A and not B. One or the other, but not both. And so if we were to depict this with and OR and inversion, all right, so this is how it would look. This is A and B not, this is A not and B, and we OR those together. Okay. Another way to do it would be like this. If you utilize the NAND gate up here, if you were able to bubble push through some of that. But anyway, that's 2 ways to do it with the logic gates that we know so far. There is a special symbol, though, for the exclusive OR gate, and it's the Star Trek symbol sideways with a little right parentheses out in front, I guess. But it's essentially the OR gate with the right-handed swoop there out in front. Okay, and then we also have a special Boolean way to write this, which doesn't, we can't really do anything with this if we write it this way. But if we say A or B exclusive ORed, that's probably how I would say it. If you circle the plus sign, that makes it exclusive. And then obviously we just showed how you could write this out in Boolean, regular Boolean. So that's a very specific equation for the exclusive OR situation. Okay? Whoops. Okay, the next one is basically taking the exclusive OR and making an exclusive NOR by inverting the output. When you do that, essentially now you're looking at the only cases where they're either both low or they're both high, right? You can see here, this output is directly opposite. It complements this output, right? Because one is exclusive OR, you take that thing and invert the output, and now you have an exclusive NOR. Okay? And so now you can see the difference in the Boolean equation. Either they're both high or they're both low. This is a very useful gate because it's called the equality gate, and you can see why. It detects whether the inputs are the same, whether they're high or low. It doesn't matter, right? That's always going to produce a high on the output. So we use the exclusive NOR gate and the exclusive OR gate for that matter, but the exclusive NOR gate essentially to see if things are equal to each other, right? The AND gate does that to some degree with just to see if they're both high, but it does not take into account the case where they're both low. So you need an exclusive NOR gate if you want to check a string of binary numbers against each other and see if there's any errors. That's the kind of stuff we're going to use this for. And again, if you wanted to put this into a logic circuit, invert both of these, put them into an AND gate, and put the regular inputs into an AND gate, so you have AB or A naught, B naught. So either they're both high or they're both low. Okay. And we just take an exclusive OR gate and invert the output. Same thing here with the special way that we write the exclusive gates. We just take the exclusive OR and we invert the entire output. Same thing here. This is the Boolean equation we just went over. Right? So both high or both low. Right? So those are the two gates. So the exclusive OR, either one, but not both. If you invert that, you get the exclusive NOR, where it detects whether you have both low or both high, and that produces a high on the output. It's just the inversion of this one. And we call that the equality gate. That's a great question for me to ask on a quiz or a test. So where do we use this? Well, one thing that we can use them in is called a parity generator and a checker. Okay, so when you send data across a transmission line from point A to point B, right, from sender to receiver, there is a possibility that those ones and zeros that you're sending could have or could be susceptible to noise on the line. And noise can happen all over the place, just, electric signals, electric noise. And so if you mean to transmit a 0 and you accidentally transmit a high because you had some voltage on the line that caused it to look like a high, that's a problem, right? So what we do is we kind of set up a handshake. The generator and the checker agree that, okay, you're going to send, you're going to send 7 bits at a time, or you're going to send 8 bits at a time, or you're going to send a start bit and then 8 bits and then a stop bit, right? There's some kind of a handshake that goes on between the transmission and the receiver where you say, I'm going to use parity to detect any errors, all right? So what happens is depending on what information you're sending over the line, if you want to check to make sure it arrives intact, okay, you add a bit to the binary information stream that's being transmitted, and then you check it on the other side to see if it's the same, okay? And the two ways we can do that is through odd parity and through even parity. Okay, so let's talk about what those are. First, let's look at a really simplified view of the parity generator and checker. Okay, so here's what happens. And it's really no more difficult than what I'm about to say. If you're on the transmission side and you are in odd parity, all odd parity means that is on the transmission side, if you count up all the highs, that's an odd number. And then if you're going to check it in odd parity, as 1, 2, 3. There's 3 on the check side, so there must not be an error, okay? On the generation side, we had 3, so that all of that information transfers over here. We still have odd parity, and so that will indicate that we do not have an error. If we were to get a different count over here, like maybe this one became a high, all right, that would give us even parity, and it would throw an error that there was data corrupted in the transmission. Okay, so that's where we're using this. So that's all it is. If it's even parity, then you just have to make sure that there is an even number of ones. Okay, now see, in this case, for this odd parity, the actual data is 0, 1, 0, 1. That's even parity. To make it odd parity, the parity bit has to be a 1. If this was 0, 1, 1, 1, 0, 1, 1, 1, that would have already been odd parity, and so the parity bit would just be a 0. Okay? So the parity bit exists to make odd parity if it's even parity. If it's already odd parity, it just becomes a 0 in the transmission. So we can set this up with a bunch of different exclusive OR gates. Okay? And so again, if it's an even parity, we exclusive OR all the inputs together, and we have a final gate of an exclusive OR. If it's odd parity, the only difference between exclusive ORing all the inputs together is that the last gate is an exclusive NOR. That's it. There's no other difference between the two parity systems. Okay? And again, this is the parity bit that's going to be generated in this case. All right. So here's an 8-bit even parity generator, and I know it's even. Well, Part of the reason I know it's even because it says right here that it's even, and it says right here that it's even. But if those words weren't on the screen, I would know it's even parity because this very last gate is an exclusive OR. Okay? Here is a 5-bit even parity generator. Okay? So even parity generator. This is a 5-bit. Okay? This is a checker. And so all of the bits come into the stream. You exclusive OR everything together. And because it's even, this very last gate, again, is an exclusive OR. Okay? All right. And as with all things, there's an IC for that. And I'm not going to go over the exact model numbers. But this is essentially like a universal checker generator, and then you tell it whether you're doing even or odd parity. Okay, and so you have an output for even and odd parity all the time. Okay, so that's one way to do it. If you don't want to connect a bunch of gates, you can just go buy an IC and have it do it. So here's what that would look like. So you connect all of these things to onto the line, onto the 8-digit computer transmission cable. Right? And so this must be a very short distance because it's in parallel, right? So it's inside a computer. And then it grabs all of those transmission lines and checks them with the even. So this is sent out, this parity bit is sent out as an input here. Notice how this one is grounded. So we send that out, all right? And then the error indicator will tell us whether or not we have any errors in this transmission. This, if I was going to do a binary parallel comparator, and I asked you to write one down on the exam, this is the one I'm going to ask you to write. Because essentially all you're doing here is you're taking two binary strings and you're determining if they are the same or not. That's a little bit different than the parity checking system here, okay? So the comparator just takes the exclusive NOR gates, remember that's the equality gate, it checks A0 versus B0. And this one checks A1 versus B1. And this one checks A2 versus B2. Okay? So as long as all of those equal each other, you AND them all together and determine if they are the same or not. If any single input is not the same as its counterpart in the other binary string, then you're going to throw an error. Okay? So if I had 0, 1, 1, 1 up here and I had 0, 1, 1, 0 down here, this gate's going to throw a 0 out, which is going to make this thing throw out a 0, which is going to be a problem. The warning buzzer will go off. So hopefully when these systems are running, you never hear the warning buzzer, because that means you never have any errors in your transmission, which is a good thing. It says, describe the operation of an exclusive OR and an exclusive NOR gate. Again, the OR is either OR but not both. The NOR is the equality gate. Okay. Okay, so the question then, does the circuit below function as an even or odd parity generator? Okay. Well, the only thing I look for is this very last gate. I see that it's an exclusive NOR, and so I know that this is an exclusive. That this is an odd parity generator. If this very last gate right here had been an exclusive OR, it would have been even. All right. So here you go. Here's like an example in Quartus. I do want to point something out because we are going to be building a comparator. I'm sorry. I haven't published it yet because I'm rewriting it for our software, right? I looked at the wording of the lab already today, and I was like, nah, it references too much of the stuff that's in the other software version. So I'm doing a pared down version of that thing, and it'll kind of be similar to how I wrote the first two. But you'll build something similar to this. So the difference is going to be, you see that this wire right here is very, very thick. This is a bus. That's the difference between just a wire connector that you see here versus an actual bus. This allows us to pull D sub 0, D sub 1, D sub 2, D sub 3. That's a binary string, the way that we type this in. And it has to be the variable name, a left square bracket, whatever the count is. So if you have 4 of them, that's 0 through 3. If you have 10 of them, that's 0 through 9. So if I had 10 elements in my string, it would be D, left square bracket, 9, ... 0, right square bracket. Okay? So this is just an example. And when I do the, I'll post screenshots of how to do this and where that comes from. All right? Let's see here. Chapter 6 is a pretty, it's important, but it's kind of a light chapter compared to what we just got done with the K-maps and all the Boolean reduction, right? So, again, the exclusive OR gate provides a high output if one input or the other input, but not both, is high. The exclusive NOR gate outputs a high if both are high or if both are low. Parity bit is commonly used for error detection in the transmission of digital signals because we don't, we can detect whether or not the parity has changed. In other words, a 0 has made its way to a high accidentally. And they're used in parity checking, binary comparison. We didn't talk about the controlled complementing circuit, but you can basically you can invert every single input if you wanted to with a controlled inverter. I think something like this. So you exclusive OR everything together, you got one control signal that's going to go high or low, and it's going to essentially invert them all. Okay? Now, I'm going to go ahead since we had such a light lecture, I'm going to go ahead and get out of this, and I'm going to go to my desktop, and I'm going to go ahead and start Quartus, and I'm going to show you how to draw those buses. So I'm going to go ahead and start Quartus. All right, so I'll just walk through this again. New project wizard. Next, I want to go change this to my C location where I know things are, and create one. I just called this one lab test. I don't really need that one anymore. But I do want a new folder, and I'm going to call this one lab. Oh, I don't know. What is this? It doesn't really matter for me, I guess. I'll just call this Chapter 6. So that's my folder. Okay, and then I'm just going to call this one Lab Chapter 6. Oh, I do want to say something real quick that me and Jonathan just went through, and that is he was having a problem with the simulation trying to run, okay? He was able to compile and everything like that. This is how he had one of his labs named. It was like Lab Chapter 6-7. You're not allowed to use a dash or any of the other special characters in your project name or your BDF file name, okay? I don't even, let's see. So John, if you're listening, I'm able to do the underscore, but I just try to stay away from all of that and just stick with, here's the other thing. This is a programming tip. So if you ever take, well, some of you are going to have to take C programming if you haven't already. If I have a file name or if I have a variable name and it's multiple words, the naming structure goes like this. So if I said, gosh, what are we doing here? We are doing exclusive OR. So if I said exclusive OR and NOR. So you can see the very first word you leave as lowercase, but every other word, you cram it all together and you just capitalize the first letter of each word so it's easy to read. Exclusive OR and NOR. Okay, or you could even say something like exclusive OR NOR. Right? So I just wanted to point that out. Empty project. I don't have anything to add. I do want to choose my proper board, which is the DA, and we scroll down to the 10M5 P0DAF484C7. There it is. Next, I make sure I choose Model Sim Altera for my simulator. Next, and that brings me to finish. Okay, as soon as my environment loads, I want to come up to the new file, choose block diagram schematic file, and then as soon as it pops up, it's defaulted to block 1. That makes me nervous, and so I come up here and say File, Save As. It automatically calls it what it's supposed to be, and I hit Save. All right. All right, so now I'm going to left-click anywhere in here, double-click to bring up the new symbols. I'm going to grab an exclusive ORs, and I believe these are XOR and XNOR. You can see them right there. So if you want to search for them, XOR or XNOR, they're right next to each other. So notice there isn't an XNOR 7 or an XNOR 10 or whatever like you have with the ORs and the ANDs. So here you're only allowed to do 2 inputs. Okay? So I'm going to create one of these and Control-C, Control-V, and Control-V. I'm going to do 3 of them. So I'm essentially doing part of the what I would call the Parity lab, which I will, like I said, I'm trying to I'm trying to revise that. So input, I just need 2. I just have 2 strings, Control-C, Control-V, okay? And I'm going to call this string, just string A, and this one string B, okay? Now I'm going to test all. I'm going to test, and again, I have to rename these again. All right. If you remember from the slide, how do I have to name this? I have 3 elements, so it has to be named like this: A, left bracket. Since I have 3, that's going to be 2, 1, and 0. So 2 dot dot 0 right bracket. That tells it's a binary string. Same thing with this one. Okay. B, left bracket, 2 dot dot 0 right bracket. Okay. That one looks funky. Give me my properties. Let me see what's going on here. I'm going to retype this. B, left bracket, 2 dot dot 0. It looks like it's in a different font from here to here. Is that a 0 or an O, or is this a 0 or an O? That's a 0. Is that an O, or is that a 0? Okay, whatever. All right, so instead of using the typical where I would draw a line, I don't want to do that. Up here on the menu bar, that's the orthogonal node tool. That's what is defaulted when you are making these wire measurements, okay? The one next to it is the orthogonal bus tool. That's what you want. Okay. There. See how it's much thicker. Okay, now as soon as you do this, you want to come back up here and click the orthogonal again. Otherwise, you're going to keep drawing buses everywhere. Okay, so you just need to, like, I'm going to connect all of the first inputs to this string here. Whoops, Control-Z that. I don't like overshooting. I like clean wires. There we go. And then I'm going to take this. I'm going to take the bottom input of each one, and I'm going to send it over to. Now, notice what just happened, right? I've gone over this before, but when I click and drag, if I go too slow, look, oh, I tried to get it in 2 places. I think I tried to do that before, too. The older versions of the software, it would let you do like every line along the way and make a connection. But here's it's a little bit more advanced. Okay. And then finally this one, and there we go. Okay. Now, I have to name each one of these individually. I'm going to go back and hit my pointer tool here because I want to select this, double-click it, or right-click it. Now, this one is A sub 0. And you have to use these brackets. I'm going to click the next one. Properties. A sub 0. Oh, that's not right. A sub 1. That's the next one. And then finally, properties. A sub 2. Okay. Now I have to do each of the B's as well. So the most common mistake here is that when you go to label this, that you label it without the bracket. In other words, you just put B0. That's no good. You have to put the bracket in there. Okay. Man, it shoved it all the way up there. Oh well. Now this one will be B1, B square bracket 1, square bracket. And B2. And then a final 3 input AND gate, so an AND 3. So I'm going to AND them all together, and then I need an output. Okay, I just need to connect these together. And there we go. Connect my output. I'm going to call this output X. Okay. Now I'm going to come up here and hit compile. Yep, I want to save. Okay, 4 errors. What don't you like about my program? I wonder if this is the error. I thought they'd fix this by now. They didn't. I am so glad that this has come up because I tried when I first started with this software to get this error to come up and I couldn't get it. And I was like, wow, that's really great. They fixed it. Well, they didn't. Okay, so you can see here when I added this symbol, it's called INST. When I add this symbol, it's called INST1. When I add this symbol, it's called INST2. Okay? Well, look what happened when I went to add this AND3. They went and named it something that's already been named, INST. So now I have to click on this or the other one, and it doesn't matter. I'll just call this INS5. Okay? That's why it's throwing a problem, because it caused its own error. I didn't do that. Okay, recompile. It's thinking awfully hard. I think it likes it this time. Okay. There we go. Now I just got to get these last 3 taken care of. As long as we don't have any errors, we should be okay. There we go. Okay, so now I'm going to go ahead and create a vector waveform file. So come up here to New File, University Program VWF. I'm going to right-click, Insert Node or Bus, Node Finder, List, pull them all over, click OK, and there we go. Now, you'll notice that the way it's presented this time is not the same way it's presented as a normal input, because you can see here that it's got that little blue, light blue, blue. It's showing that there's more than one here. So if you expand this, you can see the individual data lines. Okay. Now to test through this, I'm going to do something a little bit different, but you're going to have to do something similar when you do your lab. So I'm going to go ahead and select this binary string. And I'm going to do a little bit different count value, okay? I'm going to do radix and hex. Start value is, let's see. The start value is 7. Increment by 8. And transitions occur every 50 nanoseconds, okay? So here's what it's going to look like. It's going to count in hex from 7 plus 8 plus 8 plus 8 plus 8 plus 8. Okay, and it didn't get my transition. Wonder why I didn't get my transition. I want to increment by 8. It's not going to let me do that? Let me count the first number, but I want, oh, I know why. Because I've only got 3 bits. Let's see. Let's start at 0, count by 6s. How about that? Can you do that? There we go. Okay, and now this one, I'm going to do count value. This is going to be hexadecimal, and I'm going to start at 1, and I'm going to go by 3s. Why not? There we go. Okay. So essentially, we're going to be comparing these against each other. All right, and let's see what happens when we go to simulate. Sure, let's save changes. Yep. All right, there you go. And so you can see, you know, both binary strings have to be identical for this to click, okay? And so that only happens, you can see here, 0 is not equal to 1. These are not equal to each other. These strings are not equal to each other. If you wanted to look at them in terms of their binary value, you could do right-click, radix, binary, and then here you can say right-click, radix, binary. Now I can make this full screen, maybe zoom in a little bit, and then you can actually see at any point in time here. So 0 is the same, 0 is the same, but 1 is different. Here we have 1 is the same, the middle 2 are different, and the end are the same. So it's not until they match up exactly, all 3 bits, that you see that you get a high on the output. Okay? So what you're going to do for me for this lab is going to be almost identical, but I'm going to have you do different counts, and I'm going to have you have, you're going to have 4-bit binary strings instead of just 3. Okay? I think that's all I want to cover today, or I think that's all I need to cover. I think I got everything. And I even essentially just did the lab for you, with a few minor alterations. Okay? So as soon as we get off here, that's what I'm going to focus on is getting that edited. I'm going to put it into a newer version. I'm not even going to try to edit that PDF that was posted. Okay? I'm just going to do completely new screenshots with what I have. All right? And yeah, so if you have any other questions, just feel free to email me. If I haven't gotten to your question yet, like I said, I'm working through them. So I get a little bit more done each day, and I'm trying to create these assignments too. So, but the good news is test 2. Well, test 2, I know what questions I'm going to ask on test 2. I just do not have the questions created, and I'm also being very, very cognizant of the fact that you guys had problems last time with the formatting. Okay, so I'm trying to be extra special careful about how this looks. And so I'm going to have my parents test it out, and I'm going to have some other instructors try to get in there and test it out to log in from where they're at so they can look at it on their devices. Okay, so if no questions, you guys are free to go. Thanks for coming by, and yeah, just watch for the announcements today. Talk to you later.